Hello everyone, this is Joe again. I'm going to bring you some information about power. Probably not equivalencies today with resistances, but I'll talk a little bit about equivalencies as far as a whole system that might have an entire resistance. So the first thing I want to talk to you about is power. Yesterday I had posed the question about what would happen if a current decreased through a certain resistor, and we're talking about power. I hadn't gone over it yet, so I figured it'd probably be a good opportunity to do so before we answer that question. Now, basically, power is going to use the same concepts as your voltages and your currents. Basically, what comes in must go out. The sum of all powers is going to be equal to zero. Now, if you have the following circuit, you have a voltage at A and you have a voltage at B here. Volt is actually defined as the amount of energy required to move a unit of charge. Basically, what VAB in this case would be equal is delta W, which W stands for energy, which is in the unit of joules. I know it's a little counterintuitive, obviously, because J for joules and W for energy doesn't really make much sense. However, that's just the way it is. Now, on the denominator is the change in charge, which is in coulombs. So basically, voltage is going to be defined as your change in energy over the amount of energy required to move one unit of charge, which could be an electron, for example. And the same goes with current. Current is defined as the amount of charge that changes over time. So it's the same concept. Current is equal to delta Q, which is the change in charge, which is in coulombs, over the amount of time. So basically, how many coulombs does it passes through over a certain amount of time is basically what that is saying. Now with power itself, it's defined as the amount of energy that is changed through time. So in our case, we know that the amount of energy that's changed through time would be delta W over delta T. And how are we going to get that? How do we get that with voltage and current? Now I labeled the voltage here in red, and I measured the current in green. And then over here, we have the amount of voltage. So this one is a voltage, and this one's a current. And as you can tell, if you multiply the voltage times the current, you have delta W over delta Q times delta Q over delta T. There should be a T here. And the delta Q's actually cancel out. And the result would be delta W over delta T, which you get right here, which is exactly what we're looking for. So basically what we're looking for is voltage times current, which equals power. Should have probably said that from the beginning. You guys are probably scratching your head wondering, why'd you go through all this stuff if it's just voltage times current? Well, it's good to know, especially if you go down this field. Alright, so basically, like I said, voltage times current is power. Basically, in this case, let's give an example of what you just saw there. Let's say that you have, it could be anything in seconds, it could be in voltages, it could be in currents. However, since we are dealing with voltages times currents, what we'll say is, say there's a voltage here and there's a voltage here. Obviously, there's a voltage drop that goes across this resistor. So what you do is you take that voltage drop. So let's say VA is 10 volts, and let's say that after going across the resistor, it's 5 volts. And what we can say about that is that the difference between 10 minus 5 is equal to 5 volts. So the drop in voltage, or delta, is going to be 5 volts. And then your current, it could be arbitrary. It's really dependent on what your resistor value is, but let's just say it's 1 amp. So if there's I is equal to 1 amp, then you got 5 volts, which is your voltage drop, times your 1 amp, and you're going to be left with 5 watts. And again, the unit of power, I'm not sure if I mentioned this, is in watts, which is a W. Again, counterintuitive to energy, however, they do bring the same type of units 1 is just over time. Alright, so let's go ahead and explain this a little further. Basically, you have power. Power is going to be a number of different things. As you can tell here, I wrote down what Ohm's law is. You got voltage is equal to current times resistance. Resistance is voltage over current, and current is voltage over resistance. So if you know that power is V times I, you can literally take this and, for example, this current and replace it with this current here, and then you'd end up with something like V squared over R. Another way you could do it is if you took the voltage and you substitute it in here, then you'd get something along the lines of I squared R. So it's equals I squared R. And obviously you can keep rotating. Eventually it will just come out to the same thing. But for example, if you took this resistance and you put it into here, you're just going to get V over V times I, so you just get current equals current. So you're just going in a repetitive loop at that point, like I was stating. Alright, so let's give an example. Let's say that you have a current, a green current that goes through here. We don't know what that current is as of right now. And let's say we have a 5 ohm resistor. What we'll do is, let's just say that this right here is your iPhone 5C, obviously the yellow one, and we'll call this one your lightning cable, and this is your power supply, 5 volts. So we'll just say that's 5 volts. Now, if you look at the unit of your cube for your iPhone or your Android phone or whatever type of phone you have, or any power supply really, it's going to have a rated voltage. So for example, this one's 5 volts, and it might have like a rating for power. So for example, 5 watts would be the amount of power that an iPhone cube uses. So if you know that the answer of 5 watts, so you got power is equal to V times I. So if we know the power is 5 watts and we know that the voltage is 5 volts, what is the current? Well, in this case, we can just divide the 5 by 5 and we get current is equal to 1 amp. Now, another good way to do this is if you have, let's just say this circuit here, which is modeling your iPhone. We'll say this is 5 watts. Well, basically, if you have 5 watts, again, and you need to figure out what, 5 ohms, not 5 watts, and you need to figure out what your power is, what you can do is take the equation we have with the resistance, which is V squared over R, and then you got 5 squared divided by 5, which equals 25 over 5, which is equal to 5 watts. So that's another way to do it. Now, basically, this is a symbol of what a system may look like. For example, the iPhone system is a total of 5 ohms, so therefore it draws 1 amp of current through 5 volts in order to draw 5 watts total to charge the phone. Now, what if it's multiple systems, or what if it's not just one single resistor? For example, in this case here, let's say there's two resistors. Now, obviously, if there's 2 resistors and this is 5 ohms, and let's say that this one is 5 ohms, what is the resistance, what's the power that goes through the first resistor? We can call this one resistor A. And what is the power that goes through resistor B? Well, basically, we can use the same concepts that we learned before with KVL. And how you would do that is we have an orange I here, this current, and we know that the current is going in this direction with our ground node. So we have minus 5 volts plus 5 ohms times your current plus 5 ohms times your current, and that's going to equal to 0. So basically we have 10I is equal to 5. So you know your I in this case is going to be half an amp. So you're going to have 5 divided by 10, which is just 1/2. Now that you know your currents, this is the current of the whole entire system. So basically you're going to have that current that is half an amp is going to run through this 5 ohm resistor and also this 5 ohm resistor before terminating at ground. Excuse me. So what you're going to do in this case is, all right, well, we know that we have a 5 ohm resistor, and we know the current is half an amp. So we can say power in this case is equal to I squared R. And if I squared R, and this is just through one resistor. Since the resistors are the same, both of them are 5 ohms, it doesn't matter. One could be 5 ohms, one could be 10 ohms. To get the total power, you would find the 5 ohm power, and then you'd find the 10 ohm power, and then you'd add it together. In our case, it'd be the 5 ohm and the 5 ohm. So the first one through a 5 ohm would be 1/2, and you square that, and then you multiply it by 5 ohms. So you're going to end up with 5/4 of a watt through that one, through your power through your A. We'll just call that one A since I labeled it A. Now we know the second one is exactly the same thing. If you go through the math, it's the same exact thing. So what you could do as well to kind of check your math is, if you know the total voltage, in our case is 5 volts, and you know that the total resistance is actually 10 ohms, because you got 5 ohms in series with 5 ohms, which is 10 ohms. And so you know that basically you got 5 over exactly 10, because this part is your current and this part would be your voltage, and your voltage times your current is equal to your power. Basically 5 cancels with that, so then you get 5 halves. This is a 2, so you get 5 halves. Now, does this make sense that you get 5 halves of power through the whole entire system after we found that one unit, or excuse me, the power through A gives us 5/4 of a watt and the other one gives us 5/4? Let's find out. Like I said, the sum of power should equal to 5 halves. So we got 5/4 plus 5/4 is equals to 10/4, which is equal to 5 halves watts. So yes, it does match up. So that's a good way to check. Alright, so I'm already over on this video. I'm going to go over equivalencies next time. Basically what that will do is it'll take a resistor or a series of resistors in parallel and in series, and it will simplify it to model that whole entire network of resistors as one resistor. For example, we had the iPhone. We didn't know what the resistance of the whole iPhone was, but we measured it, and just to measure and to model it, we said, okay, it's 5 ohms. So if we had a bunch of resistors, let's just say we had one here, one here, one here, one up here, one here. Well, basically, how would we turn this into just like one resistor? And that will be the equivalent resistors. Alright, perfect. I do want to thank you guys again for watching, and you have a great day.